Okay, so hi, good evening everyone. So welcome back to plan 258. Yeah. So this is the for today. It is about IFN prioritization. So in the past few weeks, okay, we have discussed about how to prioritize your projects in transportation and urban planning. Okay, and we start with simple prioritization. Okay, with 2 by 2 matrix, and then based on knapsack, right? And then uh, we discuss also about multi-criteria decision making (MCDM). Okay, and last meeting we discussed Brown Gibson and uh, Analytic Hierarchy Process or AHP with rank reversal. So this is what we will discuss today. Yeah? So this is for next week, the following weeks. Yeah. So as a reminder, okay, after this lesson, so please do the assignment, yeah, to compare all of these methods. Yeah. Okay. And then next week, you will also have a group project presentation, right? It's a progress report. Okay. So the IFN for prioritization has been in the slide already in Moodle, so you can access. And then there is also lab. Okay. So there's also lab about IFN prioritization, something like this. So you can access also. Yeah. So this tutorial in people level 2 is a little bit old. Okay, so if you want the new one, so you go to the main level 2, but this is still under development. Go to this one, just referral.com or people referral. So and then you go to IFN transportation research. You can join the IFN prioritization. So this one need basic subscription, but if you register, I will put you free for 1 year. The rest we can just use this one. And ideal flow network. Okay, this is the book by Springer Nature. I don't know if you can see. Yeah. So this is the ideal flow network for transportation. Okay. So try to find this in SURP library. Otherwise, you can just propose to the UP library. Okay. Okay, with all of that, so let's start. Can you see my slide? Oh, I cannot see you, so I don't know. I think you need to open your camera so that I will not talk to the wall. Okay. Okay, so let's start. So first of all, this is the presentation to combine, okay, the practicality of multi-criteria decision making, okay, or MCDM method with theoretical foundation, yeah, based on Markov chain. Okay, so and then we can start to see the application of IFN, ideal flow network, yeah, which is traditionally used for transportation or artificial intelligence, okay, to the field of multi-criteria decision making, yeah, and project management. So the core question here is, do we have how do we derive the weight from raw data, okay, without subjective input? Okay, how does the IFN relate to reversible Markov chains? So this is the the one that actually start to think. Yeah, is it possible to create application of ideal flow network, okay, to compute a project prioritization? Yeah, which is similar to the table of MCDM, multi-dimensional data. Okay, but remember in Brown Gibson last meeting and ASP, okay, you have the you have to decide your weight. Yeah. Okay. One of your question was how to determine this weight from data. Okay. So in IFN, you don't need to decide. The IFN computation will automatically decide the weight for you. Okay. And then how to determine the subject. Okay, the project subject in here you need to think as project priority from data. Okay, and then what is the relationship between this IFN with the theory of Markov chain, or irreversible Markov chain? So uh, the the main discussion point here is yes, we have successfully applied, okay, IFN for transportation or other field, including AI. Okay. Uh, a new question arises whether we can actually use the same method, okay, for project management or decision science, decision analysis, and especially to prioritize our project, yeah, in transportation. Okay, so the focus in this slide will be how we will explore, yeah, that IFN can be adapted, yeah, to this emerging area of as a practical tool, right, to prioritize the task or the project, yeah, or the subject, yeah, based on data table of multi-attribute or multiple criteria. So the structure of data is something like this, yeah. So this subject, we name it subject because it can be human person, the name of the person, or it can be a project or task. It depends on you to decide the context. Yeah. This is practically the alternative of choice. Yeah. So in the row, each row represents the alternative choice subject, and then in the each column you will have variables, yeah, or the criterion. Uh, each column is a criterion, so you will have n criteria and m alternative. Is this clear? Yeah. So and then we will visualize it as a bidirectional relationship, yeah, between the subject and the attribute. Yeah. So the subject will define the attribute, and then attribute will define the subject. Let's start with a very simple example. So you have, say, data table like this. Okay, you have revenue and costs, and then these are uh, several alternative of businesses. Yeah? Either you do business or store or consultant or something. Yeah? Uh, the problem here is this revenue and cost, okay, can be independent, can be dependent. Yeah. So if you combine them together, the revenue and cost, you minus someone, you will get the profit. So in this case, profit is one dimensional, yeah, one criteria. But you can also put as two dimension if you know more data with this revenue and the cost. So uh, dependent variables with the same unit, in this case cost and revenue, okay, can be mathematically combined into one variable. Yeah? This will simplify dimensionality, isn't it? This is another example of 2D data. We discussed, this is the same data that we used during NAPSA last time. Yeah. So you have two independent variables and you have seven tasks here. Okay. So, and then for each task, you have certain effort that you measure in terms of number of hours. Okay? And then you have certain ordinal value of each task that you can put as number 1 to 10, for example. Then, of course, you cannot simply subtract or add it because they have distinct dimension, isn't it? Okay. This is another example of data. Okay. How many dimension here? Yeah, this is 4D, yeah, four dimension data. So why? You can see from 4 columns here, 1, 2, 3, 4. Okay. So this 4 column of data so represent 4D. And then interestingly, you can start to see that there are variables that uh, actually two types. Yeah? In the criteria, there are two types of variables. One is, we call it cost. Okay? The other one is called gain. Yeah? Cost means less is better, while gain means the more is better. Okay, so remember in ASP, you everything you put it into gain or just compare. Brown Gibson, you put everything into cost. Okay, but in IFN you can select either this is cost or gain, so that you don't need to convert first. Yeah? So the actual data you can put in actual unit. Yeah, you don't need to convert. Okay, you can put in actual unit, for example, days or hours, so on. Okay, and then this is another example of sport. Yeah? So here we use 6 attributes. So you have 6 dimension, yeah, 6 criteria. Okay, and then the subjects are the name of the sport tournament. For example, FIFA, NBA, so okay, and the attribute have many, yeah, including team strength, prestige, engagement, and so on. Okay, so this show the versatility, yeah, of the method beyond just simple project list. Okay, another example of 60. Yeah, say you want to similar to Google PageRank. Yeah, what is the rank of this web ranking, yeah, of certain website? So you can include all the criteria. Yeah. The important thing is you need to know, yeah, which one is gain and cost. Uh, Gain means more is better, yeah. Cost means less is better. Okay, so this is Google PageRank alternative. So up to here, what do you think about the data itself? Is this difficult to create or not? So give me feedback. So in terms of data is rather simple, right? Just the table of alternative and the factors of the attribute. And then you can put your own unit there. Any question, any comment? The data itself. And our goal is to prioritize, okay? Which subject is number 1, number 2, and 3, and then how much is more important than the others in the ratio type. So we practically convert any type, yeah, including from ordinal type, ratio type, interval, yeah, into uh, ratio type of prioritization. Okay. Okay. So let's go to the steps. Okay. So you have this kind of data table, right? And happen. Uh, this is the visual workflow. So you have the data table, something like this. Okay. And then what you need to do is simply normalize the attribute score. Okay. So you normalize, we'll practice this later, how to normalize. And then from this normalization, you compute the probability. Yeah. So now from here, you have two directions, yeah? Going to the right or going to the down here. Yeah? So going to the right, then you compute the subject utility and subject probability. Okay. Then this is the directly the prioritization of the subject. Okay. Can I throw this? Let's make it red. Yeah. So you from the data table that you have, okay, all you need to do is compute the normalization and then go into this part. Yeah. Compute the attribute probability first, and then you compute subject utility. Yeah. From utility, you get probability, okay, and then you get prioritization. Okay, so this is the part. Yeah. Simple. Yeah. So, but if you use this part, you only get what you want, which is the subject prioritization and, of course, the attribute prioritization. Yeah, the weight. Okay, that's it. Okay. From here, you can also compute the power. Now, uh, this is at this point it's just the same as Brown Gibson or the same as uh, AHP. Yeah, but IFN does more than that. Yeah, so you can also from here you can also get the actual matrix. Okay, from here also you can also get the actual matrix from for the attribute and for the subject. Okay, uh, then you will say what for? Yeah, this is to relate the theory behind the mathematics behind and the actual prioritization. Okay, and why this is important? Yeah, because once you get these two matrices, yeah, then you can start to combine, yeah, AHP with IFN with Markov chain. Yeah? And then you can reverse the process. And from ASP, you can get back the IFN, you can get back the, actually you can get back your data table. This is very awesome, which AHP cannot do, Brown Gibson cannot do. Yeah? Why? Because we have the theory. Okay. I hope you understand this to motivate first. Yeah. Otherwise, when you see the math, you will start to, ah, I don't know what is this for, right? So then you start to back up. But once you understand the motivation, okay, that this is a very awesome technique. And once you know the theory, you can combine and connect the dot. Okay. Okay. Let's start with the steps. Yeah. So the simple step first, so that you will know. Okay. Uh, so I put the 5 step here. Okay. You want to prioritize M subject. Yeah. M is the number of subject based on N attribute. This is the number of factors. Yeah. Attribute is factor. Subject here represent the project, yeah, or the alternative task. So number one, you normalize each attribute. So you focus on attribute first. Okay. From the normalization, then you compute probability. This is simple. Okay. After that, uh, you aggregate all the subject of each attribute into the score attribute. Okay, so this is the third step, and you can so that you can remember this is just the score. From the score, you compute probability. From probability, you compute priority. Just 5 steps. Okay. So the rest of this step is the theory. Yeah. Later we'll discuss. Okay. So this is optional steps as I showed in the part a while ago. Okay. Okay. So the ranking is based on probability. So this is very strong. Okay. So how to normalize? Yeah. Normalization means you want to transform your actual values, okay, with different units into 0 and 1. Yeah. You already know why. Yeah? Last week we already discussed, right? During Brown Gibson, during ASP, or even during MCDM. Okay. Because if you have different units and then different range, okay, you cannot compare, right? So in order to compare, you need to normalize, okay, in the same range. Okay. Otherwise, if you have one in centimeter, the other one in kilometer, you will have different units, so you cannot compare. Okay. So normalization is just transformation, okay, from your units into 0 to 1 range. Okay. How to transform? We just use a very simple linear formula here. Okay. So if you have gain, okay, so GI is your gain, and then you get the minimum of this gain, okay, and then you get the range, yeah, maximum minus the minimum, and then you will have NI here represent the normalized value. Okay, so this formula is useful if you're dealing with gain or benefit, yeah, meaning higher value is better. Okay. Now, how about if I have cost instead of gain? Yeah? In that case, you infer, yeah, because this is 0 and 1. No, inversion is just 1 minus this benefit gain. Yeah, simple, right? So you look at this formula, it's exactly the same. Yeah, G becomes C. Yeah, okay. So you get the cost minus with the minimum cost, and then you divide by the range of the cost. Okay, let's start with the example. Say you have costs of 3 projects, say name it A, B, and C. So let's simplify, become A is 3, B is 5, yeah, C is 2 million. Okay. So what is the normalized score? What is the minimum and the maximum among these 3? The minimum is 2, isn't it? The maximum is 5. So you know, okay. And this is cost. So cost means the formula is 1 minus. Okay, so you just put the formula 1 minus CA minus the C mean is 2, right? Divided by C max is 5, then C mean is 2. So you just put that, so you will get this value. Yeah, is this clear? Okay. So similarly, and P, uh, P is the maximum. Yeah. In that case, it will always become 0. Yeah, the maximum will become 0, maximum cost. Yeah. The minimum cost will become 1 automatically, yeah, because minimum minus minimum is 0, right? So in that case, 1 minus 0 is 1. Okay. So if you have more subjects, so you will have more computation. Anyway, there is calculator on it to compute. So up to here, is it clear or not? If you have cost, okay, you just apply the formula, linear. So you will have this normalized value, yeah? 2/3, 0, and 1. Is it clear? Okay, next. How about if we have gain? Revenue is gain, right? So let's apply the same number, okay, so that you will see the difference. Okay, so say the 3 project A is 3, B is 5, and then C is 2, yeah? The same number. what is the normalized score? Of course, the same number. So in this case, minimum is 2, maximum is 5. But remember, this is not cost, so this is gain. That means there is no 1 minus. Yeah, this is, oh, I think I make mistake. This must be G, yeah, not C. Yeah, this must be G. Yeah, yeah, this. Yeah, this is should be GA, G min, G max, and so on. Okay, but look at the number is correct. Yeah, the number is correct. This must be 1/3, 1 and 0. But look at the compare 2/3, 0 and 1. Yeah. So if you use revenue or gain, the maximum will be 1 and the minimum will be 0. Okay. Clear here? Okay. Next. Uh, we already normalize, yeah, from our score. Okay, then we need to get the score or the weight of each attribute. Okay, the weight of each attribute is just the sum of the normalized data across all subjects. So in this case, it's the sum. Yeah. So just sum of this pi. Okay, and then you compute the probability. Okay, so in this case, I suggest we use this formula. Yeah. Well, you can also use a linear formula like this, but this one have no parameter, so this is not that good. Yeah, this is better. Okay, so this is similar to a multinomial logistic model formula, logistic formula. Okay, so you can apply any parameter. Later we will see the sensitivity of the parameter. Okay, and then that weight, okay, must be the sum must be 1, of course. Yeah, the normalized weight. Okay, let's see with the example. Okay, say the example that we used a while ago, we continue. Okay, this is the normalized score, so Bij. Okay, and then you have the cost. Remember the cost a while ago was this one, 2/3, 0, and 1, right? Okay, and then the gain was 1/3, 1, and 0. Okay, so we input this into this table. Yeah. Okay, this is from the data that we set a while ago. So, and then based on the cost and the revenue, what you will do? You will compute the score for each attribute, okay, and the probability of each attribute, okay, using the formula here. Okay, so what you will do is simple. Okay, uh, first you just sum to the bottom like this. Okay, is it right? Sum to the bottom. Okay, and then you will get uh, this value, okay, divided by the sum of these two. Yeah. So this represents the probability. Is this clear or not? Is it right? So you just sum down, okay, and then you sum to the right here, and then each of this divided by that sum. Okay. So what is this? 5/9, 4/9. This represent the weight of each attribute. Okay. So remember last week, I think one of you asking how we will decide the weight. Okay. So in here, very simple. Yeah. You just sum to bottom. Yeah. After you normalize. and then you sum to the right, and then you get the probability. Up to here, is it clear or not? Is there any question? Yes, George.
Sir, I noticed in your table, sir, you usually use fractions. What if I use a decimal instead of fractions, sir? It will affect the final
Oh, no,
result,
no.
or
No, actually decimal is better, but I don't know, maybe my training in mathematics before was always use fraction because we can see integer is easier for us to see than decimal. But if you are prefer decimal, that's fine. Okay, there is no difference between fraction and decimal. Okay, okay. Yes, Andrew.
Hello, sir. Can I be heard clearly?
Yes.
Ah, okay. Sir, how can we make sure that the weight of these, yeah, the right weight is relevant to the actual importance of the variable in planning context? How do we make sure that they are more, a variable is more important than the other with
Uh,
this
it,
formula?
okay. The formula is rather simple. You just linearize the weight. Okay, but later you will use uh, the parameter. Yeah, beta. This one. So the weight itself is not so important, but you will have the weight, the beta and gamma later. Okay, then you will start to see. Yeah, when you play, then you start to see that it's not the weight that is important actually, because the weight will change automatically when you play with the parameter. Yeah, the weight is just the initial weight. What you actually want to get is not this weight, right? The, uh, but actually this weight. Yeah, using this formula. Okay, but if you use this formula without parameter, okay, then your what you asked was is correct, yeah, because how can we ensure that this is not if what if this is not linear for your project, right? So in that case, you have no way to do that, yeah. But if you change this into the this kind of softmax function, then you have a say, yeah, subjectively change this so that the weight later will represent what you want. Okay, so instead of using this formula with this linear weight, I suggest you use this softmax. Okay, so see, if you use softmax weight, okay, exactly the same table, right? And then exactly you see this one, you will see the same sum, right? Okay, exactly the same sum here, but the probability is not the same. Can you see that? The probability now depends on the parameter beta. Yeah. Okay. Diane's asking, I have attended some planning workshop in context of LCU. During the workshop, when we want to know what objective they want to prioritize, they rank it based on what they see in vision in city. Oh, that's okay. We can put this. You can practice later, yeah, and put this what each of the person in vision, okay, as the criteria, okay, and then you can also do it in group later, yeah, uh, during the practice later, yeah, yeah. Because in IFN you can also do in group, yeah. So this is actually quite awesome. Okay. Okay, good. So let's see what happened. In here, I use beta equal 1. Okay. So in this case, I will put this. So I got about this value. Yeah, about this value. Okay. And what happened? Yeah, the sum, of course, still 1. But the probability is not the same, isn't it? Okay. Probability is not the same. Depends on the value of beta that you select. So in that case, you can turn to, this is like a knob. Yeah. You want to put it a little bit bigger or smaller, that depends on you. Yeah. And later during sensitivity analysis, you will start to see, okay, uh, if you set the value of beta very large, okay, then it will start to separate. Okay, some of this weight become almost zero. Okay, some of the weight will become zero, and then the others will become like almost one. Okay, but if you put the beta very small, okay, they are almost similar. Yeah, and then beta, if you put beta is negative, okay, then the priority will be reversed. Okay, so this is the power of parameter. Okay, so let's check. Yeah, what if the probability is normalized? Yeah, uh, based on softmax compared to linear a while ago. Yeah, so using linear proportion, you will get this value. Using softmax, you will get a different value, which depends on the parameter beta, right? So, and if you check in the calculator, yeah, I'm not using linear proportion. So in the calculator, I'm using softmax directly. Okay, then you will get the actual value. Yeah, based on this probability, you can compute the utility. Yeah. So yeah, once you have these values, okay, do you want to practice what will happen if you change the value parameter become -1? You can try in Excel, just input this value, these 6 numbers. Okay, but the 6 numbers, and then what happened if you just change beta? You want to practice? Done? Did you get the same result? So when your beta is negative, okay, the weight of each attribute is reversed. Okay. So instead of 4, 7, 3, 7, now become 3, 7, 4, 7. It's the reverse. Yeah. And what happened if beta is 0? Yeah. When your beta is 0, then the probability will become equal. So in practice, you will put beta, I suggest 2 minimum. Yeah. Because when beta parameter increase, okay, the gap between the weight, yeah, will be widened because of the sigmoid curve behavior. Okay. Yeah, you can use also solver to make the sums square difference of the probability of the two methods to 0. Yeah. So in that case, you will get around 0.6. Yeah. So what happened when beta is 0? The weight will become equal, yeah, for all factors. Okay. So in practice, okay, if you want, you can try to create, yeah, what is the normalized weight, and then if you have the score, what will happen to your value, yeah, of the weight of the two factors, A and B. So this is what I am doing, and then you will see that they are practically become S curve. A and B will become S curve. When you change the beta from negative value to positive value, yeah, so the value of beta will be negative to positive, and then the value of the probability is always between 0 to 1. Okay, so let's see here so that you will see. So if your beta is 0, you will get exactly 0.5 probability between A and B. Okay? So if your beta is somewhat here, okay, so then you start to see the separation. But as your beta is very large, okay, say in here, you will see the separation is actually much wider. Yeah. So do you understand the meaning? Okay, very good. Yeah. So if you want to see separation between subjects on the uh, factor, you will know which factor is most important. You slide the value of beta, okay, to be much larger, okay? So that you will see some of this factor will go down to 0, meaning that factor is not important for you. So instead of insisting on the actual weight or subjective weight, okay, IFN compute this weight for you, and then you play with the beta and gamma later. Yes, very good question. So if the value of beta is subjective, okay, and then will it change the final ranking of the alternative? This is important, yeah. Very, very good question, George. If your beta is positive or gamma is positive, okay, there is no reversal of ranking. You can see here, yeah. This curve is important. Why? The rank will not reverse, right? See, when you this is already bigger when beta is at this point. When you go there, okay, it's just widen the gap. So the rank will not reverse, but the value of the prioritization will change, of course, based on the value of beta and gamma later. Okay, the actual weight of the prioritization or the actual power depends on the parameter, but the rank will not reverse. That's the most important part, right? In fact, when you do sensitivity analysis later, okay, you can actually control or you can actually have a clue what if I change this value in the data in order so that I can win. Yeah, it is possible. Yeah, that one is you can quote unquote cheat in your own data. Yeah, to reverse the rank. Yeah, okay, but the value of the parameter will not change the rank. Okay, it will change the weight, the scoring. Yes, but the rank will not. Why? There is the there is no crossing. Yeah, the crossing is actually in the 0 point beta 0. That's it. Yeah, you can also compare three attributes. Actually, you can compare 6, 7 attributes. There is no crossing. The crossing is always at beta equals 0. This is mathematics. Okay, always. Yeah, the crossing is always here. Okay. You want to see? Yes. Here. Let's go to the there. This one have how many? Oh, many. This is factor, and this is the subject. We have three subjects, and 1, 2, 3, 4, 6, 6 attribute. Okay, you see, always at 0, beta at 0 is the crossing. So you can just use positive beta. There is no rank reversal. Similarly with this one. From the plot, you can start to see there is no rank reversal, right? Rank reversal happen when there is a crossing between this line. And that crossing not happening when beta or gamma is positive. Yeah? Only happen at 0. That means as long as you put your value beta or gamma positive, there is no rank reversal. So it's guaranteed mathematically. Is that okay? Okay, let's come back to the slide. Yeah. So how do you compute utility? Yeah. So once you have the weight, yeah, this one, omega is the weight, right? And then you have the normalized value. The VI is the normalized value for each IJ. That means I is the row. Yeah, that means the subject. J is the column. Yeah, that means the attribute or the factors. Okay, so this weight is for the J. That means for the weight for each factor. Yeah, but this is how you read, right? So when you see the subscript here, okay, which one? J, IJ, that means row, comma, column. Yeah. And then when you sum over J, that means over all column. Okay. So meaning you sum all for each row. Is this clear or not? Yes, for the subject sensitivity after this, okay, you will also get probability. Okay. So say let's compute the example. I just use any probability here. Okay. And all you need to do is this one. For example, yeah, this is given probability. Okay. So 2/3 multiplied by this probability, yeah, and then this probability multiplied by this value, and then you sum. This is a sum product. Yeah. So this is the utility value. What is this? This is the utility UI, that means utility of each subject. Okay, so this is the utility of each subject. Okay, and then once you get the utility of each subject, how do you get the probability? Easy, yeah. Use the same formula, but different parameter. Yeah, so you use the same formula, but different parameter. So this one you use gamma for the subject, and then this one is not the not the attribute, but this is the utility of each subject. Yeah, so I'll just put gamma 1 so that easy. Okay, so the same softmax function you can use twice. Yeah, one for the attribute, the other one for the subject. Okay, so let's, this is the value, right? The utility 14 over 27, 9 over 9, 4 over 9, and 5 over 9. So I will put here. Yeah, okay, this is the utility we have computed. From there, you compute the probability. Probability is just this formula. Yeah. So once you have the probability, so this is already the ratio, isn't it? Then you just put 1, 2, and 3 here. It's okay with you. So it's done. That's it. You get the run and the weight of each run. Yeah. Changing your gamma and beta parameters will change this probability value. Okay, but will not change the run. So the larger your value of beta and gamma, okay, the gap between probability will be wider. Okay. The power will change, but the run will not. So in ASP, it will not happen. You will have run reversal. Okay? And similarly with the Brown Gibson. So this is the nice things using this formula of softmax. Yeah. In fact, softmax is used also in neural network, isn't it? So any question up to here? So if not, can you try to do this practice? Yeah. This is uh, the one that you practiced last time during knapsack problem. Remember, the result is not the same. Why? In knapsack, okay, you have another constraint which is not happening here. Yeah, in NASA problem, you have the total effort is constrained. Okay, in here you don't have that constraint. So of course the result will be different. Okay, let's try. Okay, so So what you will do, you just type these numbers, or you just copy from 2 weeks ago, 3 weeks ago, this one, the same value. And so you have 7 tasks A to G, yeah, with effort and value for each task. Yeah. So try to compare this result with your knapsack. Yeah. So what you will do, yeah, you will first normalize. Yeah, this is the normalize, and then you get the weight. Yeah, you get the exponential, and you get the normalized weight, meaning the probability of each factor. Yeah, and then you will get the utility and the probability of each task. Okay, so try this first before we go to the next example. Peter, you want to share your screen? So actually, in the lab, you already encoded, yeah, all the practice in the slide here. So this is the first practice, exact data 352, right? And then this is the result. And this is the second practice that we okay. So this one, uh, this is the value, and then this is the result of the prioritization. So this is another example. Say you are you want to hire this subject, for example, 4 subjects, and these are the criteria that you set. Okay. You see that they are different units, right? And so once you have that, so you can just compute, calculate, and you will have result. So if you want to change the parameter beta and gamma, so you just change here. Or you just set your number of subject and attribute, and then you create a new project. Now, the calculator also have a goal seeker. That means if you want to do exactly like knapsack uh, last time, so you can do that by changing here. Yeah, so just add the constraint. So let's come back to your 2D task. Okay. And I want this is the 2D task that just did. You do a goal seeker. What do you want to do? Something to do. Goals to the data. 2D task. Then goal seek. Okay. So just add constraint. What is the total constraint in the knapsack last time? 10. Is that correct? For the F1. So then you just click optimal. So you will get similar to the knapsack result. Uh, you want the sum to be less than this is maybe you just put less than because there is no equal here, so you can just put and compute or still the same. So you can just change the statistic and change. So you can remove the constraint and add more if you need. Yeah? This is just add once. Now, given this prioritization, right, the result, you get the utilities and the probability. Okay, what happened is there is something nice here. Okay, you can see the sensitivity view. Yeah, if you click this sensitivity, you will see the sensitivity view. That means for each factor, there is something range. Okay, so that means if you change this value beyond this range, the rank will reverse. Do you get it? Okay, let's start to see what have. This is the result is A, C, G, right? Okay, and from here, the value of A is from 0 to 4.9. Okay. What happened instead of 4.9? Okay, what happened if the value of A, the number of hours is 5? That is beyond 4.9, right? Okay, there. You will see the sensitivity of this should be supposed to be 0 to 4.95. Now you change it to 5. What will happen? Okay, so then the rank will change. The rank will not be the same as before. So it's not the parameter that changed the rank reversal. It's the value that you in. Okay. Another example so that you will see clearly. Say you want to hire this 4 people based on this criteria. So you are the committee, yeah, of hiring, yeah, HR. Okay, and this is the salary asked by that person. So what happen if you click here? The allowable of Alex is between 0 to 216. Yeah. So you know this is computed automatically by the program. That means right now Alex is number 1, right? But if Alex asking more than this value, Alex is no longer number 1. Let's try it. So what will happen if Alex asking for 250? It is beyond this value, right? Okay. See, Alex is now number 2. Nice. Huh? Okay. Yeah. So say, and then you can also have a group. Huh? So group conversion means you can add the voter. Okay? So you can practice later. You can add the voter. Yeah. And then you can also show the conflict. So for example, you have 2 uh, person in the group. Okay? So just name the stakeholder A and B, and then you can A say 7, yeah, for this value, but B will say this is not 7, this is 8. So you just save. Okay. Similarly with this value, if this is the same or not. So if there is a difference, it will show there is a conflict map here that show this is actually different. Okay, so if you close this, okay, it will have a group icon here to show that this is actually a group fault. Okay. Any question? Yes, Lester.
Sir, good evening. Just for clarification, should the utility value be multiplied by the softmax probability or by the linear probability?
So the utility, you just put it into this softmax value. This is the formula. U here, UI is the utility of each subject I. Okay, and then you multiply by gamma, it is constant, and then you take exponent. Okay? And then you do that for all subjects, and then you sum. Okay?
Yes, Prof.
Yeah.
I'm pertaining to the value of the utility itself.
The utility itself is just this one. The weight of the factor. Okay? The utility is just simple formula. Okay. Utility of I is just the weight of its factor. This is the probability of its factor multiplied by the normalized value of its factor.
Yes, Prof. So the probability or the weight of its factor could be either linear or the softmax value.
But better you use softmax so that you can change the beta parameter.
Okay, Prof. Since in this example you use the linear in getting
Yeah.
the utility, and then on the second example you use the softmax value.
Yes. Yes.
Thank you, Prof.
Okay. So I hope this is clear enough. Yeah. Computationally, it's easy. Yeah. Just put in the Excel and then compute. Number one is normalize. Yeah. That normalization based on either cost or gain. In the calculator, you just click, it will become cost. Click again, it will become gain. It's toggle. Yeah. Yeah. And then once you get the weight of each factor, yeah, multiply by the normalized, you get the utility. Yeah. This utility, you sum product, yeah, for all J. That J means criteria. Okay. So be careful with the subscript so that you will know I represent the subject, J represent the criteria. And then you get all of that. You get probability of each subject. Yeah. So I is the subject. So you get the probability of subject. Yeah. Then finish. Once you probability, you just sort, you get the rank, right? Yeah. Quotation is rather simple. Yeah. Last year I did the same thing, so I did not make the calculator. So yeah, the students just use Excel. Yeah, you can get exact the same value. Okay. Did you get exactly the same as this one? Yes. Okay. And how about the rank? Okay. So if you compare this with the knapsack, the result is not the same, yeah, because we don't have the constraint. Okay. Okay. Let's go to the comprehensive example. Okay. So far this is what we did, yeah. So you have the data table, right? That you set on your own, and then you normalize the score attribute, okay? And then you compute the attribute probability, yeah, using softmax, yeah. And then you compute the subject utility, right? And then you compute the subject probability, and then prioritization, yeah. That's it. Okay. So let's go now with this more comprehensive example. Say, with how how do I get the 5/9? Because that part is because of the uh, I'm using linear or using softmax. Yeah. Okay. Okay. Very good. So yeah, very good, George. Yeah. Okay. Yeah. So let's practice this. Now we are practicing using 4 4D, yeah, that 4 dimension. That means 4 criteria, and you have only 5 projects. Yeah, let's name it project A, B, C, D, E. Okay, so I keep the value here. Yeah, so you want to prioritize these 5 projects. Okay, based on effort, customer satisfaction, urgency, and resource availability. So urgency means that the number of days until the deadline. Resource availability means the number of workers. So they are different units. These 3 are gain, okay, and effort is a cost. Yeah, remember the normalization depends on whether it is gain or cost. Okay, so you will practice this. I will give you time. You will practice this in a group. Is that okay? Within your group, okay. And I will just show this example first so that start to see. Yeah. So then what you will do? Yeah, you normalize. Okay, so this is the value. Then you normalize for each column. Yeah, because you know the maximum and the minimum of each column, then you normalize. Of course, because you normalize, so there must be one of them must be 1, one of them must be 0. Yeah? If it is cost, okay, so the minimum will be 1, the maximum will be 0. If it is gain, the other way around. Okay? Up to here, is it clear? Next, once you have this, next step is you sum. Yeah? After you normalize, what you will do, you sum to the bottom. Yeah. Okay. So this is the score. Yeah. This is the normalized score. Now, once you have this normalized score, what you will do, you compute probability. So this is the score at the bottom. Yeah, I just copy here. Yeah. Okay. This is the. And then you compute. This is the sum, right? Okay. And then you take the E exponent, yeah, of beta times this score. So you will get this value, and then this is the sum, right? And then each of these, for example, 16 point something divided by 60, you will get 27. Yeah? 12 point something divided by 60, you will get 20%, and so on. So here is it. Okay. So once you have the weight, this is the weight of each factor, yeah, and depending on the parameter beta. Yeah, in here beta is set. And then after you get the weight, yeah, I copy again. Okay. This is the normalized factor, right? What you will do, you compute the utility. Yeah, utility is just the weight. So this is just the same as MCDM table. Yeah. So the weight multiplied by each row of this. So this is just the sum product. So you get the utility as a sum product, right? And once you get the utility, what you will do? Okay, you compute the probability of each project. Yeah. So yeah, this is the utility, and then you just make it exponent. Yeah, and then compared to the sum, 1.889 divided by 8, you get this probability. Yeah. If you look at the probability, they are almost the same. Why? Because I put gamma and beta 1. Yeah, if you want to make it bigger, then they are separated later. Then you will see better. But the rank will not change. Okay. So try this. And then, of course, the rank is simply based on the probability. And the power is just this probability divided by the minimum. Yeah. Okay. So let's try. Okay, before we go to the next point, so I'll give you time, okay, to go into your group and then do this. And then you can discuss later when you finish, okay, you share and then give me the result and maybe more question, yeah, because you have done this in the group. So I will open rooms. Okay. There is no menu to open the room. Maybe I should close this sharing. Oh, there. Breakout rooms. How many groups do we have?
4, sir. 4.
4. Okay, I will create 4 rooms. Okay, and I will let you choose your own room, yeah, based on your group. So open. Okay, we will come back here. How many minutes do you need? 10, 15, 20,
15.
15. Okay, go. So 7:45, 17 minutes. Okay, go. Okay, so how is it? You want to share your work or have some comment, question? What was your discussion about? Yes, Apple.
Sir, we would like to present our work po.
Okay, go.
Ah, so for this, sir, we type first the values on the left side, and the normalized values are here. So we use the maximum and ano, maximum. Sorry, I think I
Yeah,
have, yeah.
one minus.
Uh, yes, sir. Then after that, we computed for the sum and the exponential of the sum. Then for the normalized weight, I think I have to add more, something like that, sir. Is this for the normalized weight? The total of the exponential of the sum will divide the exponential for each, sir.
Okay,
So
so
I'll be applying this for others too. And then after, sir, for the utility, we multiplied the normal this to the values of each, sir. Is this
you just use some products.
some products, sir? Okay.
Uh, can you check if the normalized weight, the sum of normalized weight is 1?
Sum of normalized weight. Yes, sir.
Okay,
Okay, so for the utility, we can use the sum product
yeah, some product, the
product
normalized weight.
sum product of
Yeah, that row
this row and
and the
this, sir.
normalized weight. Yes.
Okay.
And then you put the dollar sign for the normalized weight,
Okay.
9, dollar in the 9.
Okay. Dollar and
Then copy down.
yeah. Okay, sir. Then for this column, we just get the exponential of the utility for each.
Right.
Then for this, for the probability, we divided
By
each
the sum.
exponential by the sum of it
Right. You just,
in percentage form.
okay. Good.
Then for the ranking, we use this formula.
Hmm.
So I think the first is the task B, second is task D, and A next. For the fourth one is C, and the last is E.
Oh, I got different result from you.
Maybe we should recheck again the values we've included in this part, sir.
Okay.
We'll review this again.
The utility is not the same.
Utility.
Ah, I see. This is for the cost, but for the ordinal urgency, the ordinal value is not the same.
Ordinal value. For this, sir?
Yes.
Okay, sir. I'll revisit this again.
Yeah.
Okay, sir. I'll edit it first, sir.
Okay.
Okay, thank you, sir.
Thank you. Thank you. How about the others? Anyone want to share? Mhm. Andrew?
Uh, C2 minus min. C.
Hello, sir.
Yeah.
I'm sharing my screen.
Yes.
Okay, so
C2
uh, we just
minus.
recreated the same in the slides.
Mm-hmm.
Uh, we got the same sums,
Okay.
and then uh, my groupmate Diane tried the
Uh,
website,
okay.
and we compared by changing beta and gamma.
Okay.
So we got this ranking values.
Uh, did they change?
Uh, it's consistent with, yes, it's changing depending on the value of beta and gamma.
The rank change? Ah, because your gamma is
When
negative.
no, we this one retained gamma equals one. For we just played with the the value,
Okay.
and we somehow have the same. I think we recreated it in the Excel, so because it's the same value ranking with the website.
Hmm. If
Uh,
gamma or beta is negative, then the rank change. But why? Why the rank is not the same? 2 and 3, A
where,
and B
sir?
change. A and this one, the column N and column O.
Column M. This one, it's updating if
I
I
mean,
what
this column.
if we set gamma to one and beta to one,
Uh,
the this M column changes. Then we just manually type the ranking here,
okay.
just to record all the ranking depending on the beta and gamma values.
But the rank changed, no? This one.
That's our observation. I'll test right now. Beta equals 2. The probability updated. Rank 1 is project B. Rank 2, project B. Rank 3, project A. Then same 4 and 5.
If 1, 1,
F1, 1. Uh, rank 1 is project B. Next is project A. Then project B.
that
Then project C and E.
there is a change in the rank. How about this one? What is the value of this one?
Which one? We set gamma to 2 and beta to 1. So gamma set to 2. So rank 1 is project B, then project A is rank 2, and project B is rank 3.
I see.
Same rank 4 and 5.
I see. That's interesting. So there is still a reversal of the rank, but not number one, yeah, number 2 and 3, right?
2 and 3, yes. I'm not sure how to interpret this.
Me too, not sure. I thought the rank will not reverse by the change of parameter, but apparently uh, you just did proving that I was wrong. Yeah. Let
What?
me check. But no, I'm just trying to be objective. So maybe my understanding is wrong. So I may need to check this further also.
Okay, sir. Thank you.
Thank you. Changing the beta affect the run, but not when changing the gamma. Probably. Maybe the interaction between beta and gamma that is the one that changed the run. So, as usual, when we do research, we assume something, but when the fact actually against our uh, assumption, then we need to change. No? Okay. Unless we prove mathematically. Okay. Good. So other groups. So I'm also learning from you. Okay. How about the other groups? Two, yes, Lester.
Actually, sir, we have the same observations with Andro.
Mm-hmm.
When we change, for example, beta
Mm-hmm.
with value of 2,
Mm-hmm.
the rank interchange.
You can.
The project D became rank number 2, while project A became rank number 3.
So
And then it stays as we increase the beta. For example, we have a beta of 10.
it's the same.
There's still there um were changes. The
Mm-hmm.
rank 1 now is project D, and
Mm-hmm.
then rank 2 is project B, and then rank 3 is project A. So the retained ranks are project C and E.
Okay.
Yeah, they are
Oh,
ranked 4th and 5th.
okay. So I guess its parameter will not change the rank, but the interaction between the two parameters will change the ranks. No? Hmm. Because the curve when we do change, for example, you put beta just one number, for example one, but gamma
Yeah.
you change, it will not change the rank, right?
Yes, even if we change the gamma, for example, we put value of 10 in the gamma.
As long
So
as it's positive, so it will not change.
yes.
But once you change value of beta, it will change the rank. Oh,
Yes.
so that's mean the interaction, yeah, between the two parameters. It is the one that created change of the rank. That's interesting. Oh, I also learned from this, no? So thank you. Okay. Oh, that's interesting discussion. At this point, I don't know why and how we will keep the interaction down. But that's very interesting to research it further. No? Super. Any other, the last group? What group did not present yet? Thank you, Lester. I think we have 4 groups, right? Oh, you presented all already?
Hello, sir. Maybe my group mates can present since I'm joining via phone right now, but we already
Oh,
shared the file
okay.
due to technical difficulties.
Okay. Hmm. But there will come a time when the RAM will not change one. It reaches certain. Oh, really? There is a certain. What is the value of beta that will not change the RAM? Large value of beta. Okay. How is it? Okay. So Lester said if beta value is 6 and larger, okay, the RAM will not change. That's interesting, because that happened because when the value of beta is very large, okay, then it really separates the factors. Can you try that the probability of the factor become very big gap between small and the big one? Okay, yeah, that is interesting. And this is what we call research, no? So we try and then we make a hypothesis, okay? And if it fails, or we objectively find why and probably find the best interaction. So at this point, yeah, thank you, Lester. He said if you want the rank will not change, so put the value of beta very big, yeah, maybe 6 or 10. This is still hypothesis, yeah, but I think this is a practical hypothesis. Do you still want to present, Paul and the group mate? Or maybe just the same?
Hi, sir.
Yes.
Roger.
Yeah. Go ahead, Roger, if you want to present. Mhm. Okay. Okay, this is the data. And then, so you get this and you get the weight. And then from the weight, you can get the utility. Okay. From the utility, you just need to compute the probability. Okay, you haven't finished. Okay. Yeah. You just need one more step to compute the step 5. Yeah. Just to compute the probability. Yeah. Using a parameter gamma. Yeah, maybe the time I gave not enough. Sorry. It's okay then. Thank you, Roger. Oh, so the ranking is consistent with beta set to 1. Oh, really? When beta reaches 5, the project D become brown. Okay, so the value of beta, the ranking depends on the value of beta. That's interesting. Thank you for your report. Project D is very sensitive. Let's see. What is this? 4 dimension. Is that correct?
Yes, sir.
Okay, let's see the 4 dimension. This one, right? Is this the one that you put? So we can check the sensitivity here. So if I change the value of beta, you said 6. Okay, so B, D, A, rank 1 is B. Is that correct? And then B, D, A, C, E. Yeah? I change this to 6. Oh yeah, it changed. B, D, A, C, E. Still the same. Changing the value of beta. Okay, I've changed this to 1. Calculate. B. This one changed. Rank 2 and it's changed. So the sensitivity of T, this is the one that very close. If you see the range, customer satisfaction and urgency, these are the one that very close. Also, this one is very close. From 5.5 to 7.9, very close. That is probably the one that make the value sensitive. Yeah, I think this is interesting to research this further. Yeah. Okay, let's go to the slide. Yeah, so you know how to compute. Yeah, computation is easy, right? Pretty straightforward. Yeah. Okay. And once you have that, let's go to the theoretical aspect. Yeah. Theoretical aspect. So we already have this part, right? But we did not go here. Yeah. So this is the one. So this part and this part we did go. Yeah. So this is the one that we will explore here. Okay. So this is just copy earlier. So this is the 5 steps earlier. We normalize, we get the probability of each attribute, right? And then you get the aggregate all the subjects, yeah, based on the score, and then you compute the utility. The last step is to compute probability of subject, so that you get the priority. So this is the normal way to compute. See, but let's go to the theoretical aspect, which is the bottom. What is the connection of this with IFN? Okay, so because we have 2 things, one is the subject, and then we have also the attribute. So each of these we will compute as a stochastic matrix of IFN. Okay, and then from the stochastic we compute the ideal flow matrix. Yeah. Yeah. And then surprisingly, okay, the priority is just the same as the sum of row or the sum of column of the IFN matrix. Okay, so if you go to the website, if you don't register, you can just use this one. So this is the analysis, right? So you go to the bottom, you will see this is the normalized score. This is how we compute, right? Normalized score, and then this is the weight, right? And then this is the utility probability of the subjects. And then there it is. Yeah, this is the stochastic matrix. Yeah, and the ideal flow computed there. Can you see? Yeah. So how do you get the stochastic matrix? This is just copy, yeah, of this value, this probability. Yeah. The final result of this probability, just copy, you will get the stochastic matrix. And then this is just 1D stochastic matrix. That means you copy once for all the factors, and then each row will be exactly the same. Yeah, so the total must be 1, right? Because it's probable. Same thing for stochastic matrix of the subject. You get the probability of the subject, and then you just copy. Yeah. So this one. This is the probability of the attribute. This is the one that you copy, yeah, into this value. Yeah, this one. Yeah. From here, from the stochastic matrix, and then you compute the ideal flow. Yeah. This is just based on the Markov chain. And interestingly, if you see the ideal flow matrix, yeah, this is the flow between one attribute to the next. Yeah. You will see that the sum of rows of ideal flow matrix is always exactly the same as this one. Yeah, this is interesting. Yeah. So this sum of row is the same as sum of column, and then exactly the same as the stochastic matrix. Okay, similarly with this one, the sum of row in subject ideal flow matrix is exactly the same as the sum of columns, and also the same as this value in the stochastic matrix. Okay, so yeah, so here I formalize. Yeah. So to set the 1D stochastic matrix, okay, you already have that probability of each attribute. So you just copy and then repeat, yeah, the first row up to n times. And for the subject, the same thing. Yeah. So you get the probability of each subject, and then you repeat. Yeah, because this is 1D, so just copy down. Okay, something like this. This is the example. Yeah. So this is the attribute, right? So you get this probability, yeah, of the attribute of factor. Okay, I copy this here and then copy down. Okay, so this is the stochastic. The same thing. This is the probability of each subject. Okay, I copy this, but I need to transpose, yeah, because this is, so 21.72, 24.35. So I copy the first row, okay, and then I copy the first row down. Okay, so if you have this stochastic matrix, okay, so what you will do, you can go to computational ideal flow matrix based on the stochastic. Yeah, you can go to tutorial of IFN. Here, if you have the stochastic to ideal flow, yeah, this is the actual way to compute. So you just enter the stochastic matrix here, and then click this blue, and you will get the flow matrix. Or you can check the actual value here in this pattern. And this is the actual network of this flow matrix. Is this clear? So when I say stochastic to ideal flow, you just use the computation to get the ideal flow. And then the priority is exactly the same as the sum of row or the sum of columns. So let's call this pi. And then the relative power is just the pi of each subject divided by the minimum priority. So this is example. Okay. So this is for the factor. This is the value, right? And then if you compute in calculator, you will get the ideal flow matrix. And the sum of row, okay, is exactly the same as this, the first. Each row of this stochastic matrix. See this exact copy. The same thing with the sum of column is exact copy. So when you see exact copy, that means there is a pattern there, right? Okay. And not only that, okay, the ideal flow matrix becomes symmetric. No? Oh, this is very important pattern. Okay. The F, meaning the ideal flow, becomes symmetric. Okay. And the Sij here is the same as this one. So this is very interesting pattern, at least in theory. But you will say, what is the meaning of this symmetric discovery? It shows that this is actually a process. So this is for the factor, the same thing for the subject. The subject exactly the same. So you get, you see, this is 21.72. This is also 21.72. This one also 21.7. And then the ideal flow matrix is also symmetric. You see, this is exact symmetry. And more interestingly, the diagonal value of this ideal flow matrix, this is also a pattern. What is the pattern here? The diagonal value, okay, this is quadratic. There. The diagonal value is a square of arc ratio. This is very interesting pattern. At least mathematically, you will see that this is actually the diagonal entry of ideal flow matrix relate to the square of arc ratio of the column itself. This is the theoretical result that you can get based on the prioritization that you can connect to ideal flow matrix. Because the matrix, the ideal flow matrix is symmetric. Okay. Yeah. In this book, I show mathematically that this is actually the same as reversible Markov chain. So this is to connect the dot. What is Markov chain? Markov chain is a very powerful tool to model any system actually, where the past and the future state are statistically independent given the present state. So this is called memoryless. So that means the future state depends only on the current state. Tomorrow depends on today, not depends on the past, not depends on the past history. This is the main assumption of Markov chain. So if you know this ideal flow network is basically a Markov chain, and symmetric Markov chain represent what is called reversible Markov chain. So there is a special Markov chain that is called reversible Markov chain. What is this? This is meaning the chain will behave the same whether it is forward or backward. So the transition probability from one state to another is equal to the probability of transitioning back to the original state. So this is there is a property called detail balance to prove that this is actually reversible Markov chain. So reversible Markov chain itself is a very powerful tool to understand the modeling of any system, basically, that the future and the past are statistically independent. So when you have the Markov chain that satisfy what is called detail balance equation, okay, that means the probability of being in one state to go to the next state, say currently in state I, go to state J, that is exact probability from state J come back to state I. So mathematically, we just put like this. So the probability, this is the current state, and then you have the probability from I to J. That is the same as probability from J multiplied by the probability from I to J for all. So this can be put into the formula. So this is the pi I is the sum of row in ideal flow matrix. This is the sum of columns in the ideal flow matrix. And pi j is the sum of column in ideal flow matrix. And then this is the Sij is the value of the stochastic matrix a while ago. So when you multiply, this is exactly the same. So this is what is called reversible Markov chain. So our Markov chain is actually irreducible. That means from one place can reach any other state in finite number of steps. So the graph, if you put it into a network, will become strongly connected. From one place, you can go to any other place and come back. That's the meaning of strongly connected. Okay, so the key property here is all reversible chains are irreducible. But be careful, not all irreducible chains are reversible. So the time reversibility, this is the main component of this MCDM based on IFN. Okay, so this is the mathematical proof that when you have ideal flow matrix which is symmetric, this will become if and only if. That means two direction. Yes. If it is Markov chain is reversible, then it must be symmetric. If it is symmetric, then it must be reversible Markov chain. This is the proof. Both sides. Very strong theorem. Okay. So that means, okay, because our IFN is actually symmetric, and we know that symmetric IFN is the same as reversible Markov chains. That means we can conclude that the 1D capacity matrix or the stochastic matrix a while ago is related to the reversible Markov chain with detail balance condition. Okay, so what does this mean? This proves that our ranking method a while ago is actually balanced and stable. It's not arbitrary heuristic values. Okay, so the theory back up the ranking, not just arbitrary ranking. Okay? It's a physics. So usually we can get reversible Markov chain. This is the example. We can get the symmetric from either symmetric and doubly stochastic matrix. So when we say doubly stochastic, that means the sum of row and the sum of column are all one. This is also if you have symmetric and doubly stochastic matrix, then usually you will get reversible Markov chain. This is in physics. But be careful. Symmetric ideal flow. These are two examples, counter example. Symmetric ideal flow does not imply symmetric stochastic matrix. This is two example of symmetric ideal flow, but the stochastic matrix are not symmetric. Okay, and you see this is half, this is 1, so they are not symmetric. So be careful, not always symmetric. Up to here, is there any question? So in principle, okay, we would like to say that, look, the theory of the ranking based on IFN, okay, is backed up by physics. I mean, theoretical physics. Not just arbitrary ranking. It's the main conclusion there. Okay. And next, we can relate IFN prioritization with ASP. This is the next one. You have learned ASP last meeting, isn't it? Yeah. So in ASP matrix, you have reciprocal matrix, right? And then you set the value 1 to 9. Yeah, and then the other one is the other side of the triangle is 1 over, right? Okay. So say you try this one to input this as a capacity matrix, then you will get symmetric ideal flow matrix. So, and this is the theorem. So if you have a reciprocal matrix from ASP, as your capacity matrix, it will always produce symmetric ideal flow matrix, if and only if moving two sides. If the matrix of the reciprocal is 100% consistent. Okay, so this is the proof. So so this is the reciprocal matrix C is consistent if and only if there is priority factor, right? This is what we did last week. So, and then reciprocity, meaning that this value means 1 over. If Cij is equal Wi divided by Wj, okay, and Cji equal to Wj divided by Wi, because this is reciprocal, that means 1 over, isn't it? This is by definition. Okay, so when we say consistent, okay, that means if you multiply the sum, the product must be 1. Okay, if this is not 1, that means inconsistent. Okay, so then we normalize. Okay, so to get the value, we normalize the sum of columns. Okay, and then from there we can calculate the stochastic matrix based on the normalization. Okay. This is just to construct the stochastic matrix, and then from there you can get the stochastic matrix. And because remember this is one stochastic matrix, so you will get the pi directly. Remember earlier, the pi is the same as here. This is the pi, right? It's the same as this value. Can you see that? See, this value is the same as this value. the sum of column, the sum of row. This is the prioritization probability. It's the same as this one. Exactly. Okay. So this is what I just proved here. So the pi is the same as the stochastic. So the transition matrix depends only on the I. Yeah? You will get exactly one this stochastic matrix. Yeah? So this proof that you will get exact consistent. Yeah? As long as you have been consistent ASP matrix, that means you will get back the IFN. Yeah. So with that, yeah, now you can also create a new index similar to ASP, okay, but definition is not the same. Yeah? So you will have inconsistency index or consistency index, yeah, yeah, based on IFN, okay, which is if you don't use that detail balance, okay. So what does it mean? Okay, so if you have AHP, okay, you can connect to the IFN, okay, and then you can connect to the actual data. So isn't that interesting? Okay, and then you can also get the inconsistency index, yeah, based on the ideal flow matrix. Yeah. Okay. What is this? Because when you try to do changing the value, okay, from the consistent, okay, then you will get skew, yeah, not symmetric anymore, right? Then the one that skew compared to the symmetric, that is the one that inconsistent. Yeah, that's mean the noise compared to the total signal. That's meaning when we define the inconsistency index, unlike Saati, yeah, arbitrarily create, and then after that, oh, still wrong, and then adding a new table, right? RI index. Okay, so because they try to create arbitrary values, so then they need to correct. Yeah? This one is based on the theory. Yeah, so then you will get inconsistency index. So let's try this. Yeah, let's try this in practice using the lab, so that you will see. Not this lab. This lab. Yeah. So can you see? I will use your example, Marco, the one they just did, right? So this one in the reverse engineering, there you can see the ASP matrix here. Can you see this? Okay, you can see the ASP matrix. So for either subject or for the factor. Okay, this is a reciprocal matrix. Okay? Or if you don't like in the matrix form, you can also use slider view. Okay, this is the one that your respondent is trying to answer, isn't it? 1 to 9. Huh? So then what happened if, so I will check this one, pedagogue. Yeah. So what happened if at this point your inconsistency index is 100%. Yeah. If you use IFN, it's automatically compute, okay, consistent, 100% consistent. That means zero inconsistency. Yeah, the theory back up that. Yeah, so consistent, 100%. This is the value that I show. So what happened if? Oh no, because I'm subjective, right? I want to change that. Okay, no, I'm comparing resource availability and customer satisfaction. No, I will change this value. See, when I change this value, can you see the inconsistency in that change? Okay. Okay. Can you see that? So no, I'm changing this. So now you can start to see, okay, how much is your inconsistency in your own decision. Isn't that cool, huh? Right. Okay. So every time you change this, okay, it will change the inconsistency index. Okay. So at this point, irreversible. Yeah. So you can reduce. Just slide this one, and then you can reduce. Interesting. Now, uh, not only that. Okay. When you click this button, okay. Okay. You remember our value, right? This one. Okay. You already copy, right? This copy in your Excel a while ago, right? So what happened if I change this based on certain thing that is inconsistent, 19% and so on. So I click this button. There, it will change the value. It will change the value, yeah, to reflect, okay, your subjective opinion down there. Wow. See, because this is reversible. Can you see that point now? Cool. Yeah. If I change, okay, whether it is consistent or not, okay, I can reverse the value. This is something that ASP cannot do, isn't it? Huh? Okay. And then the next thing that probably will blow your mind is, okay, what happens if I don't check this pedagogic mode? Okay. No, I'm forcing, okay, the real thing. What if I force this to be, say, this is what I want. Okay, 32% inconsistency. Okay. Something wrong with my human point of view. Okay. But I want to make this consistent back to the data. Is it possible? Wow. Okay. So it is possible using IFN. So what you will do, yeah, what you will do is uncheck this one. This is pedagogy, yeah. So I will make this 0, yeah, by changing the data above. So click this one. There. It will change the value of the data, of course, not the original, but it will become exactly similar to what your slider talking, yeah. It will also change the slider a little bit, okay? And then it will make the value exactly 0. Cool. Right. So with this, you can design your 0 inconsistency index. Awesome, isn't it? Yeah. So back and forth. Wow. Okay. Very cool. Okay. So yeah, the rest is just the theory. So it's just check, yeah, whether it's true or not. The one that we computed a while ago. Every time we try, we need to check whether the theory backup is correct or not. If not correct, then you can report to me. Yeah. Either my code is wrong or maybe the theory have some problems. So no problem. Okay. This is what is called research. No? So we keep improving over time. But so you can see the value. And not only that, okay, when you change this is the value. When you change that into asymmetrics, a while ago, okay, I will try again. Yeah. So when you change this, say, to 23%, then this value is the one that create the inconsistency. So you will see. Yeah, this is the one that create inconsistency. So you can change it. This is the factor, and you can also change the subject. Yeah, this is the one that create. Oh, the subject still is the same. So I did not change this value, 0, right? So what happened if I change this become 8%? So then you go down, then you will see this is the value that changed. Yeah, this is the one that create the inconsistency a while ago. So we can check also. Okay, so getting deeper and deeper. Yeah, I know this is probably we see, this is too much theory. But look, the theory is the one that back up the actual result. Yeah? If you just want practical, simple, right? All you need to get is only the rank. Okay, but once you get the rank, so what? Yeah, and then you will argue, you will fight each other. Okay, but once you see the theory, okay, then you can start. Hey, what do you want? You can start to debate. You start to discuss how to make it consistent or not, how much consistency or not. So you can check. Yeah, and not only that, you can also do this. Yeah, and you can also log. Yeah, you just I think you just click Alt, yeah, and then Alt and here. This means the one that you lock this one will not change when you reverse back. Okay, so I only want to certain value that change, but the one that you lock will not change. So you can also Alt and then click this one. Yeah. Say for example, this one should be 5. Okay, and then Alt click. So that means lock. Okay, and when you click this one, there, it because it's locked, it will not change. I don't know. This is interesting or not. I guess. Yeah, for me, it is very, very interesting. Yeah, that you have the both, yeah, the theory and the practical. Yeah, practical thing is rather simple. You just get the probability and the rank. That's it. This is exactly the same as MCDM. Yeah, the same as ASP. Yeah, but the one thing you don't need to check the you don't need subjectively decide the weight because a IFN compute the weight automatically, isn't it? Of each factor. Yeah. So that is also one of the advantage, yeah, of IFN prioritization. So as a conclusion, yeah, so this is IFN can be used as a MCDM, yeah, tool to prioritize the subject and the attribute based on simple multi-dimensional data. Yeah, and this is actually very unique, isn't it? You can see a lot of uh, many uh, pattern, yeah, inside this IFN. Yeah? So, and you can also see that there is very rich theoretical foundation, yeah, that connect the dot, yeah, between physics, between the IFN, between MCDM, yeah, and then many other things. Yeah. Once you get the IFN, actually you can do a lot of other analysis, yeah, including cycle, pivot, signature, and so on. Yeah. So, and remember, when you use IFN analysis, you are not just prioritizing, yeah, because the rich theoretical background support you. Like Isaac Newton said, the one why I can see further is because I yeah, stand in the shoulder of giants. Yeah. So the rich theoretical uh, background of this, yeah, based on physics. That means physics is like how many centuries, no? Yeah, based on the Markov chain, which is already how many centuries. Yeah. So we stand in the shoulder of many giants. Okay, so I hope this is interesting and useful for you. Okay, and for your theoretical challenge, if you like, so you find a counter example of symmetric stochastic matrix that does not produce symmetric ideal flow. So with this, we finish our lesson for today. Yeah. So you can register if you want to get that access. Okay? You will get one year free to the enterprise level. Yeah. So $99 per month. Okay. Yes, Andrew, you want to ask me something?
Hello, sir. I would like to ask, what will be a good example of a workflow when we apply what you taught from survey to discovering that there is rank inconsistency, and then we force the backward pass into a new data table. What do we do with the data table in the planning process?
Uh, in your thinking, what do you do in this case? So you
Uh,
collect the data, right? After you collect the data, okay, you input this. Your collect data is data table or in ASP form. If you're collecting data in data table, it's always consistent, 100%. Okay, so once you get the rank that you have, correct? Then you can use the ASP form, the slider a while ago, to check whether this rank in both factor and the subject, okay, then you start to compare pairwise comparison. Is this the one that you want? Right, subjectively. Yeah? So you can also discuss in a group. Is this the one that you want? Okay. If not, then you can slide. Okay. Now, when you slide that, it will automatically become inconsistent. Not 100%. Yeah? Have certain inconsistency. So if your inconsistency is still say below 10%, so maybe still okay. Right. And then what do you want to do? Depends on you, right? So you said, oh, in that case, I may want to modify my data table earlier. Okay. So the one that I got from the data. Then you can lock certain value that, no, this cell I don't want to change. Okay. This cell I want to change. Okay. What will happen? Then you just click that, you will get the reverse. So this is interesting now because you have reversible Markov chain. So you can reverse back, right, to the data. Okay. And then certain value in your data will change to represent either that inconsistency or you can force into zero inconsistency. Two sides. Okay. Depending on which button you check or click. Yes.
so, sir, when we date the data table to be consistent or zero inconsistency,
So
we adjust the project's factors to match that data table. Is that the
the point is like this.
one way?
No, the point is if I want it to be consistent after you do the subjective slider, okay, okay, if I want to make it consistent, what will be the data table that reflect that slider? Okay, but if you just do one way forward from data table, it always consistent. Be careful. Yeah. From the data table, yeah, it always become 100% consistent AHP. That's the theorem a while ago that I showed, right? That the AHP consistent is exactly the same as IFN, if and only if. Okay, but if you change, okay, in the ASP, then it's no longer consistent. Okay, then you can ask, if no longer consistent, I want to know. Okay, I have my data a while ago. I want to know what the change in the data that make it inconsistent. And then you can also make it, okay, if I want to force this to be consistent, what is the change? So there are two questions there. So is this clear or? Any other question? Maybe feedback. So comment, problem, no question. Yes, Joyce.
Sir, this is only clarification, sir, for next week presentation. So because you mentioned that we need to create a strongly connected network and formulate an optimization model. Does this mean we should already apply this prioritization method like MCDM in our group project? Or
Yes.
we will focus more on linear programming, something?
No, including this one. Okay. And then in your group project, can you start to identify who are the agents, the stakeholders? And what are the factors? Okay. And then can you start to think for each stakeholder, who influence who? Who influence who and how much? Okay. Just roughly is okay. Just rough estimation in your stakeholders. Okay. Who decide this project? And from whom to whom? And it must be strongly connected. That means, for example, oh, this is for the people. Yeah, so people is one of the stakeholder, right? Okay. The community. So that community become the stakeholder. Oh, okay, from the politician up to the community. That means, okay, you need to come back. Yeah, from each node should be come back to an in other node. The influence, either short term or long term, it doesn't matter. But you need to throw the arrow that it come back. It should be a feedback loop. Why? Because this represent monitoring system. Yeah. So who being monitored? Yeah. For example, the boss supervise the staff. Yeah. And then eventually go to the customer, for example. Yeah. So then the customer will give feedback, either maybe direct feedback or simple feedback not to buy that product. Right. So that is also feedback. Yeah. Or telling bad things or good things about that product or ratings. And that's also feedback, right? So the customer influence whom? Maybe influence the product. So the product becomes stakeholder. Not necessarily people. Project itself can be the stakeholder. Okay. And then that stakeholder influence whom? Do you understand? Yeah. So when we say stakeholder, not necessarily human, not necessarily institution, can be the project itself. Yeah. Don't forget to include who is the target of that project. for example, the community, the people, or the yeah, agent that you set up. So I want to see the whole big picture so that you can start to see who influenced who and what is the decision. Yeah. The actual number, the actual data, it doesn't matter. I said in the very beginning, okay, you can just make up your data, okay, but just make it consistent. Okay, so it's more our practice rather than getting data and then show this. Even if you focus on the data and then you cannot compute, you cannot understand all these concepts, so it's not so useful. Okay. Once you understand the concept, then you go to the real world, you just collect that data. That's easy, just data input. Right. Okay. So don't focus on collecting data. Focus on understanding the concept. Yeah. Data can be simulated. Is that okay? Okay, good. So there is assignment and there is what? Uh, Presentation. Yeah, next week for groups. And the one who did not do the last week assignment, so please do. Minus 1% per day. Okay. Okay, so thank you very much. Yes, Andrew, you want to ask? Or
Sir, one last. Would like to ask about the method regarding normalization. What if the maximum and minimum value is unknown?
oh,
Do we have to just normalize, uh,
that is,
compartmentalize in what we have?
yeah, that
Or
is that. I have a tutorial on Refoleto normalization. Normalization tutorial. You just type that in Google. Tutorial. See there. Let me show you. Okay. So when you type Refoleto normalization tutorial, so this is the tutorial about two types of normalization. One is mathematical normalization. The other one is uh, statistical normalization. Okay, so the mathematical normalization means you put in the range of 0 to 1 or -1 to +1. Yeah, that's also another possibility. Okay, and if you look at this, say your real value is d, okay, and then you don't know. That is to answer your question. Yeah, you don't know the actual range of minimum and maximum. Okay, in that case, you just use that value, okay, and then you can just say, this is the formula that I created, no? So I just put square here, and then I just add with any number positive, yeah, a is either 0 or positive, okay, and then you just take the square root. Then this is normalization. It will always become 0 to 1. Okay, of course, this function is not unique. You can just put any function actually. Yeah, so say this is another function that I created, okay, just to show I don't know the minimum and the maximum. That's exactly my problem before. Yeah, I want to know if I don't know the minimum and the maximum, then how I normalize. So easy. All you need to do is just create something and then put it something down that is much bigger than above. Then it will become always between 0 and 1. And I plot this, it will become like this. Yeah, depends on the value of t. Yeah. So it will become between 0 and 1, you see? Yeah. Interesting, yeah. So do I answer your question? So not necessarily, if you know, then you use this, of course. This is the usual. This is linear. Huh? This is non-linear, you see, the graph. So if you use this, this become linear, yeah? Or if you don't know or if you know the minimum, and the minimum must be 0, then this will come no more, just d divided by d max, isn't it? Okay, automatically. Be careful. This is linear. Yeah, the one that I set there is actually linear. The value is linear. Okay, so I hope this. Now, what if I don't want that? So I don't know the range. Okay, another function I can just sum. Okay, I just sum all of this, define. Then you will always get between 0 and 1. Again, if you don't know the range. Or you don't like that sum, okay, you can just take the absolute first and then you sum. It's the same. So there are many functions that you can create, yeah, just to make it 0 and 1. Okay. Or you can square it. And there is a breaker test. Is that if you have only 2, you can just minus and then you sum. This is another way. There are many ways to create normalization. Okay. So I hope this is useful enough. And if
Thank you, sir. I will just review the website.
if this is wrong, so you can also do this. Yeah. So at least you get the idea. Yeah. Okay. So interesting pattern. Yeah. So next time we can discuss about this one, statistical normalization. Yeah. You just remind me, and then I will discuss with you about this. Yeah. And this is also interesting. Yeah. Okay. So see you next week.
Thank you, sir.
Yes.
Thank you, sir.
Bye.
So